আওয়াজ করিও না, এখান থেকে যাও। Okay, good morning, good afternoon, and good night to everybody. Today, this is the actually seventh class of Physics 1, Waves in Elastic Media. The topics covered here: what is wave and types of wave, actually basic concepts of wave, mechanical wave, superposition principle, wave velocity, power and intensity in wave motion, interference of wave, complex wave, standing waves and resonance, and we'll solve some real life example. So today we'll discuss the chapter. So first chapter, first this is the actually we'll discuss the chapter 7. This is the seventh lecture, and waves in elastic media, and we'll cover this criteria. First of all, we'll try to understand what is wave and classification of waves and wave properties. This is actually the ocean. In every sea, we get these types of waves. Actually, why are able to see? Actually, because there is a light. Why are we able to see? Actually, because there is light. And what is light? Actually, light is a wave. So, what is wave? Now, we see some real life examples here. Someone waving in a playground and someone surfing against the ocean. So, this is the surfing, and surfing is a real example for a wave. So a wave is a disturbance that carries energy from place to place. So in a short brief, we can define a wave. Wave is a disturbance that carries energy from place to place. So a wave does not carry matter with it. It just moves the matter as it goes through it. Okay, that means there is no transfer of matter. মানে পদার্থগুলো এক জায়গা থেকে আরেক জায়গায় যায় না, জাস্ট পদার্থগুলোকে না মুভ করায় ওয়েভ. So some waves do not need matter, that means called medium, to be able to move, for example, through place. They are called electromagnetic waves. This is the example. And some waves must have a medium in order to move. These are called mechanical wave. So what is mechanical wave? Some waves must have a medium in order to move. These are called mechanical wave. Suppose sound wave is a mechanical wave because this wave cannot transfer from one place to another without medium. That means air medium or air medium. So sound wave is actually mechanical wave. So types of wave, there are actually two types of wave. One, first of all, transverse wave. So what is transverse wave? Waves in which the medium moves at right angle to the direction. Actually, this wave moves at right angles. This is why this is called transverse wave. And initial position of particles like this, but after wave, this is the initial position of particles, but after wave, the wave of the position of particles moves like a 90-degree angle. Curve obtained by joining the displaced positions of the particles. Okay. So parts transverse wave. In this transverse wave, there are two parts. One is crest. The upper topmost portion is called crest, and lower part of portion is called trough. So crest is means the highest point of the wave, and trough the lowest point of the wave. So another one is compressional or longitudinal waves. Waves in which the medium moves back and forth in the same direction as the wave moves. Suppose vibrations of a particles, and this is the actually direction of wave. And after, first of all, this is the normal position, but after waves, this compression, rarefaction, and compression, rarefaction. That means this is the density, the position here, the densely, but here rarely. So in densely, we can define compression, and in without dense, it's called rarefaction. So compression, rarefaction, compression, rarefaction. In this way, the wave moves along back to forth. So these types of wave is called longitudinal or compressional waves. And the compressional waves also can be seen like this. Compression, this is rarefaction. Compression, rarefaction. So compression and rarefaction of a longitudinal wave, regions marked C and the compression and rarefaction marked R, rarefaction. So parts of a longitudinal waves, compression. What is compression? Where the particles are close together. And rarefaction, where the particles are spread apart. So this is the compression, densely, and rarefaction, not densely. Okay, the particles closed in densely, but here the particles are not closed. This is why rarefaction occurs. Now wave properties. Wave properties depends on types of energies making the wave. Wavelength. What is wavelength? The distance between the one point on a wave and the exact same place on the next wave. This is the wavelength. This is the distance between one point to a wave and the exact same place on the next. This is actually called wavelength. So this is for transverse wave. This is for longitudinal wave. Now frequency, how many waves go past a point in 1 second? Unit of measurement is hertz. The height of the frequency, the more energy in the wave. 10 waves going past in 1 second, that means 10 hertz. And 1000 waves go past in 1 second will be what? 1000 hertz. And 1 million waves going past is called 1 million hertz. So what is amplitudes? How far the medium moves from rest position where it is when not moving. That means remember that for transverse wave, the highest point is the crest and the lowest point is the trough. This is the amplitudes. This is the most distance of the crest. And this is the most distance of the trough from the axis. This is why it's this length is actually equal, and this length is called actually amplitudes. Bistar. Amplitudes means bistar. So this is for transverse wave and this is for longitudinal wave. Okay, crest, trough, crest, trough. This is that for the all transverse wave. Now I have to remember in that for a compressional wave, the points where the medium is close together are called compressions, and the areas where the medium is spread apart, that means not densely, is called rarefaction. So in this case, we can see the displacement like this. This is the compression and this is the rarefaction. So the energy of wave is proportional to the square of the amplitudes. So mathematically it can be written as E equals to, that means energy equals to amplitude whole square. Where is the energy? Capacity, and C is a constant depending on the medium and is the amplitudes. For example, if the amplitude is equal to 3 units, then C equals to 1. In that case, energy will be 9 units. So for different amplitudes, we'll get the energy, and figures will be like this also. So note that when the amplitudes of the wave is 1 unit, the energy is 1 unit. And when the amplitude is doubled, the energy is quadrupled. When the energy is 10 times greater, the energy is 100 times greater. So what is wave speed? Depends on the medium in which the wave is traveling. It varies in solids, liquids, and gases. A mathematical way to calculate speed, wave speed equals to wavelength multiply frequency. That means B equals to F lambda. B equals to F lambda. So if wave has a wavelength 2 meter and a frequency 500 hertz, what is wave speed? Actually, this is the changing wave. Speed equals to 1000 meter per second. Reflection, changing wave. If the surface is flat, the angle at which the wave hits the surface will be the same as the angle at which the leaves the surface. This is the law of reflection. This is the refraction. Actually, this is for light wave. And diffraction will be like this. The bending of wave around an object. This is the different example. So in that case, we have actually gave an example of waves, and this is the actually surface waves of in motion. So this is the disturbance and carries energy from one place to another, classified by different categories. And what is mechanical wave? The energy is transferred by vibrations of medium. That means medium means matter. So electromagnetic wave is the energy moves through the disturbances in the electromagnetic field. So this is the wave structure, amplitudes, and this is the crest, this is the trough. So making a pulse requires a medium, the material through which disturbance is moving is to transfer energy. This is the example of mechanical wave: sound, water, rope, spring, wave, etc. Pulse, direction of energy transfer, vibrations. There are three types of actually wave. One is longitudinal wave, another one is transverse wave, and third one is surface wave. Actually, wave of ocean is called surface wave. Longitudinal wave, sound wave is the actually longitudinal one, and this is the transverse wave, which transmit energy at right angle. And surface energy, ocean energy, and surface moves. This is the transverse wave, sideway or up and down. Earthquake waves, and electromagnetic waves or light waves. Longitudinal waves, the sound wave, actually back and forth, compression, rarefaction occurs. So this is called longitudinal waves. Wave describes the earth. Characteristics of wave. Waves are described according to their amplitudes and wavelength. That means this distance, this length. What is wavelength? Is a repeating unit called a cycle. Velocity, speed equals to how fast wave travels. And wavelength will be determines the color we see. Pitch. This is the wavelength, length per second. And velocity will be B equals to F lambda. We have learned. And mechanical waves travels faster through the dense. This is the frequency. Frequency measured by the unit hertz. And B equals to F lambda is the actually for speed. How long amount of time for one wavelength to pass a point. So this is called period. So actually we have discussed the wave motion here. We also discussed what propagation in wave. The answer is question to the physical condition due to the disturbance generated at some point in the medium is propagated to other points in the medium. In all the waves, the particles of the medium vibrates about their mean position. So this is the characteristics of wave motion. Wave motion is the disturbance produced in the medium by the repeated periodic motion of the particle of the medium. Only the wave travels forward, whereas the particles of the medium vibrate about their mean position. So there are actually 4 characteristics. Now there are actually mainly 2 types of motion, transverse and longitudinal. So we have also discussed about what is transverse and what is the longitudinal. We also discussed this motion. Now we also define actually the wavelength. We also define this term. This is the actually wavelength from A and B, this length. And it frequency, what it is also, we also discussed what is amplitudes, what is the time period. And time period means it is the time taken by a particle to complete one vibration. Suppose frequency is when time taken to complete n vibrations equal to 1 second, time taken to complete one vibration will be 1 by n second. Actually, according to the definition, this is the time period. So capital T equals to 1 by n. And vibration, what is vibration? And what is phase also? This is the definition of phase. Now relation between frequency and wavelength, velocity equals to distance by time. So velocity equals to what? Wavelength divided by time period, lambda by t. But frequency multiplied time period equals to what? N. Capital T equals to 1 by n. In that case, B equals to n lambda. This is the example to calculate how far sound travels while the fork complete 30 vibrations. So n equals to 400 given hertz. This is the frequency. P equals to velocity 320 meter per second. Lambda equals to watt. So B equals to n lambda, and equals to actually frequency 0.8 meter. And distance traveled by the wave when the fork completes one vibration 0.8, and when 30 vibration multiply 30. So properties of this is the properties of longitudinal progressive wave. There are actually 10 properties. B y equals to S sine twice pi by lambda bt minus x. This represents the equation for simple harmonic wave motion. And now we'll discuss differential equation of wave motion. The general equation of simple harmonic motion was y equals to S sine twice pi by lambda bt minus x, and differentiating one with respect to time, we get what? Dy by dt. So A will be the constant, sine differentiation will be what? Cos. So but with respect to time t, this is why twice pi by lambda is the constant, and b is also constant. So differentiating this is actually velocity, and this is the after differentiating equation two times with respect to t, we get d square y by d t square. This is going to minus 4 pi square ab square lambda square. To find the value of compression, differentiate equation 1 with respect to x, dy by dx. This is the actually rate of compression. That's by a cos this. To find the rate of change of compression, another differentiation, and 2 times differentiation of 4, we get this. So from equation 2 and 4, we get dy by dt equals to minus b dy dx. From equation 3 and 5, we get d square y by dt square equals to b square d square by dx square. This equation represents the differential equation of wave motion. Now, the general differential equation of motion can be written as d square y by dt square equals to k d square y by dx square. Here k equals to b square and b is the root over k. Knowing the value of k, the value of the wave velocity can be calculated. Now, particle velocity and wave velocity. So this is the actually simple harmonic motion wave equation of simple harmonic motion, and b is the velocity here. And now the velocity of particle u equals to dy by dt. The differentiating equation 1, we get the velocity. Maximum velocity of the particle will be what? At 0 degree. Cos 0 degree equals to 1. Okay. So maximum particle velocity equals to 2 by a lambda multiply wave velocity. To find out the particle acceleration, 2 times differentiation of this. So we get actually this one. To find the maximum acceleration at y equals to a will be what? Maximum. So maximum will be this. Sin 90 degree equals to 1. The negative sign shows that the acceleration of the particle is directed towards its mean position. Now differentiating equation 1 with respect to x, dy dx will be given by this. And dy dx represents the slope of the displacement curve. Okay. So this is the, from the equation 2 and 6, we get the velocity dy dt equals to minus b dy dx. That means particle velocity at any instant equals to wave velocity multiply slope of the displacement curve at that instant. Now distribution of velocity and pressure in a plane progressive wave. This is the actually equation of wave. Now particle velocity dy by dt, thus differentiation. Now if the medium is in the strain in the medium, strain means actually বিকৃতি, কোনো মাধ্যমের বিকৃতি যদি এটা হয়, dy by dx is positive, it represents a region of rarefaction. If dy by dx is negative, it represents a region of compression. The bulk modulus of the elasticity will be this. So we get the value will be, this is the actually direction of propagation, and this is the whole complete lambda, and this is the displacement. So this is the half and this half. So complete one cycle. So this position is 1 by 4, and this is the t by half, and t by 4, t by half, 3t by 4, and this is the complete t time period. So this is the velocity dy by dt calculation. And this is the compression, and this is the rarefaction, and this is the compression. Energy of a progressive wave. We have to calculate the energy of a progressive wave. A progressive wave motion, there is no transfer of medium in the direction of propagation of the wave, but there is always transfer of energy in the direction of the propagation of the wave. Analytical treatment. The equation of a simple harmonic motion is this: the velocity, particle velocity u at any instant, this, and this is the acceleration. That means 2 times differentiation. Differentiating equation 2 with respect to time, we get this. Actually, this sign indicates that the acceleration is directed towards the mean position. Now, potential energy, what will be? To move the particle from its mean position to distance y, work has to be done against acceleration, work done for a displacement dy, f dy. So rho is the density of the medium. The work done per unit volume for the displacement dy equals to this one. So the total work done of the displacement for the displacement y will be this. This is the total work done. But y equals to this, potential energy per unit volume will be this. This is the constant 0 to y dy dy. And after integration of y with respect to y will be y square by 2. Okay. So potential energy is this. Therefore, potential energy will be y equals to sine 2 pi by lambda bt minus x. Now, kinetic energy per unit volume will be half rho u square. U means what? Initial velocity. So potential kinetic energy will be half rho u value, putting the value of u. So kinetic energy, we get this equation 5. So total energy, what will be? Potential energy plus kinetic energy. Just taking common sin square theta plus cos square theta equals to 1. So energy equals to this, where velocity equals to n lambda. So putting the value of B, we get equals to twice pi square rho n square a square. The average kinetic energy per unit volume and the average potential energy per unit volume are equal. So each is equal to the half the total energy per unit volume. Suppose an average and kinetic energy per unit volume is this, and average potential energy is this. So suppose the area of the cross section of a parallel beam of a radiation is 1 unit and velocity of the wave is the b. So velocity volume equals to what? 1 multiply b, because the cross section area is 1. So energy transfer per unit area will be EB. Just putting the values. So energy transfer per second is also called the energy current per unit area of cross section. In this way, we get energy transfer per unit area. Now, this is the example for you, 4.2. At time t equals to 0, a train of waves has the form. This is actually equation of wave. The velocity of the wave is 30 centimeter. So this is the second example. This is the second example. At a time t equals to 0, a train of waves has the form this. The velocity of the wave is 30 centimeter per second. Find the equation giving the wave form at time t equals to 2 seconds. So y equals to s n twice pi small t by capital T and x by lambda. Actually, this is the standard form of equation of wave. When t equals to 0, we get this one. So y equals to 4 sine twice pi x by 200. Just comparing equation 1 and 2. Comparing equation 1 and 2. Actually, I equals to 4, lambda equals to 100, t equals to twice second, x equals to 60 centimeter. So y equals to this. Similarly, we can solve this example. When a simple harmonic wave is propagated through a medium, the displacement of a particle in centimeter at any instant of time is given by this. Calculate the amplitudes of the vibrating particle, wave velocity, wavelength, frequency, and time period. This is the standard form, general equation of simple harmonic wave, and this is the given equation. Now comparing these two equations, we get a equals to 10 centimeter and lambda equals to 100, b equals to 36,000 centimeter per second. We know n equals to b by lambda, okay, and n equals to 360 hertz. Time period will be this. Similarly, we can solve another example, this one. Similarly, we can also compare this equation. 4.6 also can be similar example for you. And 4.7 also same formula. Here n equals to 512 hertz, a equals to 0.25 centimeter. This is the actually displacement, amplitudes, rho density, b equals to velocity. So total energy per unit volume is 2 pi square rho n square a square. And energy transferred across a square centimeter per second will be this. Just putting the values, we get this one. So the velocity of longitudinal wave in gases. Consider a long tube of area of cross section A. Let A and B be two cross section of the tube. Suppose the region of the normal density, the medium moves from right to left along the length of the tube with velocity u. The sound waves travels from left to right with the velocity u. In such case, velocity of sound, this is the first surface and this is the second surface. So part A and this is the part B. We will try to find out the velocity of sound. Now, this is the position. So as there is no change of the average density of the medium, the masses of the medium crossing the section A and B 1 second are equal. So mass of the medium entering a cross section A will be AU rho, and mass of the medium leaving the cross section area AU1 rho 1. So mass equals to AU rho. If B is at a region of condensation, its density will be higher than the normal density rho. So rho 1 greater than rho, U1 less than U. In that case, so the momentum per second of the medium entering at A equals to mu, and momentum per second of the medium leaving B at B point mu1. So the momentum per second, change in momentum will be this. The change in momentum per second is due to the difference between pressure. We get this applied force. According to the Newton's second law, of rate of change of momentum is equal to the applied force. So this is why we get equation 1. Substituting the values of m, au rho, and u1 by u, rho by rho 1 from equation 1. So we get equation number 2. The bulk modulus of the elasticity of the medium E equals to this formula, but volume is the proportional to the 1 by rho. In that case, therefore, B minus B1 by B equals to 1 minus rho divided by 1. In that case, E equals to this one. So from equation 1 and equations 2 and 3, we get U square rho equals to E and U square equals to E by rho. So E equals to root over E by rho. This formula is true in the case of plane waves where the original disturbance of various small amplitudes. This requirement is fulfilled by the sound waves of ordinary intensity. The relation also holds good for the velocity of simple harmonic plane waves through the homogeneous isotropic medium. Again, Newton's formula for velocity of sound. The velocity of sound in medium, solid, liquid, or gases depends on the elastic and density of the medium. Similar formula, E equals to root over E divided by rho. Where U is the velocity of sound in the medium, E is the elasticity, and rho is the density of the medium. Now, if initial pressure is P, initial volume is capital B, increase in pressure P, decrease in volume small b, final pressure will be capital B plus B, and final volume will be decreased B minus small b. So, we must know P plus B, B minus B equals to PB. Just multiplying. So the final volume is we get PB is negligible due to for very small quantity. So capital P, small p, capital B equals to capital P, small b, or P equals to we get. So from the definition of elasticity of the medium equals to what? Elasticity, change in pressure divided by change in volume divided by original volume. P divided by strain, volume strain. So PB divided by small b. From equation 1 and 2, actually, we get equals to P. Substituting equals to P in the original formula, we get equals to root over P by rho. Where taking normal pressure, P equals to 0.76 meter of Hg. So 0.76 meter means what? 136 multiply 1000 into, so 9.81. The density of air will be at normal temperature 1.293 kg per meter cube. Just putting U equals to, we get 280 meter per second. The experimental value determined from the various experiment gives the velocity of sound at normal temperature will be 332 meter per seconds. So this is the experimental value. So we need to actually Laplace correction for that. According to Laplace, when sound waves travel through air, there is condensation and rarefaction in the particle of the medium. Where there is condensation, particles come near each other and are heated up. So during the diabatic process, PV to the power gamma equals to constant. So initial pressure capital P, initial volume capital V, and change in pressure small b, and change in volume small b. So PB to the gamma equals to P equals to change in pressure and B equals to change in volume to the power gamma. But we get after calculation, just taking P common and B to the power gamma common, we get PB will be cancelled from both sides. So we get this expression. Now neglecting gamma PB divided by capital P, capital B, we get this relation, or gamma P equals to this. From the definition of elasticity, we get this. So equating equation 1 and 2, we get equals to gamma P. So substituting this value equal to gamma P in the equation, U equals to root over E by rho, we get this. Here gamma is the ratio of the between the two specific heats of air or gas. For air, gamma equals to 1.42. Now the velocity of sound at normal temperature will be 332, which is the value of agreement with the experimental value. Hence the correct formula will be this. Now effect of temperature. So according to the 0 degree, this is the formula, and according to the 3 degree centigrade, this dividing by this, we get root of, U is proportional to root over T. That means the velocity of sound in air or gas is directly proportional to the square root of the absolute temperature. Now calculate the increase in the velocity of sound in air degree Celsius in rising temperature, or prove that the velocity of sound air increases by 0.61 meter per second for each degree Celsius rise in temperature. So dividing by the equation, ut divided by u naught equals to root over t capital T divided by t naught, but capital T equals to 273 plus small t. Just calculation like this. Similarly, we can find the result. What will be the when the pressure of gas is doubled and its temperature raised 157.5 degrees centigrade. Just using the same formula, we get the result. And this is the number 3 formula. The velocity of sound in air at 16 degrees 340 meter per second. Find the wavelength lambda. Okay, we get lambda 2 equals to u2 divided by n. Find the temperature at which sound travels in hydrogen with the same velocity as oxygen at 1000 degrees centigrade. So gamma to be the same for the two gases. Capital T1 will be this, capital 2 will be what? So this is the value. Now effect of pressure. The velocity of sound in air is independent of change of pressure. That means volume equals to mass divided by density. So we get PV equals to constant if the experiment is the temperature is constant. Since the mass contains constant, pressure divided by rho is constant. So from the formula of Laplace correction, U equals to root over this. So this is why this is the constant. Therefore, the velocity of sound in air or gas is independent of change in pressure. That means do not depend on pressure. Effect of density of the medium. For the two medium of density rho1 and rho2, for the first formula, this was the first density rho1, and second formula will be for the second media. So now dividing by 1, dividing 2 by 1, we get U equals to root over 1 by root over rho. The velocity of sound in air or gas is inversely proportional to the square root of the density of the medium. So effect of humidity, the density of water vapor at normal temperature will be 0.8 kg per meter cube, where is the density of the dry air is this. Therefore, the water vapor has the density less than the density of the dry air. Consequently, the density of the moist air is the less than the density of the dry air. As the velocity of sound is more in a medium of lesser density, so the velocity of sound is in moist air is more than the velocity of sound in dry air. Similarly, effect of wind, we can get it will be a decreases the velocity of sound in air due to the effect of wind. Now prove that the velocity of sound in hydrogen is 4 times the velocity of sound in oxygen. The density of oxygen will be d1 and the velocity will be e1. Density of hydrogen will be d2 and the velocity will be u2. So just d1 by d2 equals to this 4 times. Velocity of sound in water. According to the Newton's formula, this, and velocity of elastic water is this, density water 1 gram per cc. So equals to 1493 meter. The velocity of sound is water is approximately 4 times the velocity of the sound in air. So another example, the equation of transverse wave on a stretched string is this. Write down the equation of wave that wave produces a stationary wave in a string or superposition with the given waves. Uh, this is the given wave y equals to this, and y1 is the incident wave twice by 80 another wave. The reflected wave will be y2 twice this plus this minus this plus. This one will be the reflected. The resultant of y1 wave will be stationary wave. Now interference of sound waves. Consider two simple harmonic waves y1 and another is y2. The b is the velocity of propagation of each velocity wave and lambda will be the wavelength. So the resultant displacement of the particle due to the superposition y equals to y1 plus y2. So y equals to this and y2 equals this. Now you must know y equals to this plus b into this. This means what? Sine a plus b formula. Sine a cos b plus cos a sine b. In that case, we get y equals to this one a plus b cos pi, this one b sine pi. Let a plus b cos pi equals to a cos theta and b sine pi will be a sine theta. In that way, capital A equals to root over this and tan theta will be this. So capital A equals to just squaring both sides and adding these two equations. Root over a square b square twice ab cos pi and tan theta, that means just dividing these two equations. So a tan theta equals to b sine pi divided by a plus b cos pi. This is equation number 3 and this is equation number 4. Therefore, capital Y equals to this one. So equation number 5. The resultant vibration has the time period, the frequency and wavelength. The amplitudes and phase difference are different. So when phi equals to 0, twice pi, and that means n times twice pi, etc. And a equals to b, capital A equals to root over a square plus twice a square. In that case, capital A equals to twice a. Intensity of sound will be I equals to amplitudes square, that means 4 square. Therefore, the intensity of sound maximum at these points and where the two waves differ in phase by n multiplies twice by, or the path difference is n lambda. Here n equals to 0, 1, 2, 3, etc. And when phi equals to pi thrice pi twice n plus 1 into pi, etc. And a equals to b, then amplitude equals to 0. Intensity of sound equals to 0. Therefore, the intensity of sound is minimum at those points where the two wave differs in phase twice n plus 1 into pi, and the path difference will be this. So for frequency, as for n 0, 1, 2, 3, etc., special case, the two waves of the same difference amplitudes at the same direction having the phase difference 0, a equals to b and phi equals to 0. From equation 3, a equals to twice a. So capital A equals to twice a and angle will be 0. So from equation 5, twice a sine twice pi by lambda bt minus x. The resultant vibration has the amplitudes twice a. So in this case, condensation and rarefaction are coincides. When two waves of the same frequency and amplitudes travel in the same direction having the phase difference pi. So a equals to b and pi equals to pi. So in that case, amplitude equals to 0 from equation 4, angle also 0. From equation 5, y equals to 0. The resultant vibration has 0 amplitudes and medium remains undisturbed as shown. This is the resultant. This is also resultant for this. When two waves of the same frequency and amplitudes travel in opposite direction, the interference phenomenon gives rise to a standing or stationary wave as discussed earlier. So